Math 1343, confidence intervals. Estimating one population proportion. Another example. A sample of 250 products from an assembly line revealed that 3.2% of them were defective. If it is possible at 99% confidence for 5% of products to be defective, production is shut down and machinery is recalibrated. Should production shut down? This is an example of a quality control word problem. You are responsible for the quality of products being manufactured at a plant. So periodically you take a sample of them and measure what percent of them come off defective, and under certain criteria, shut down production, fix the problem, and move on. In this particular company, the criteria for shutting down production is at 99% confidence, is it possible for 5% of the products to be defective? In the context of a confidence interval, we're saying if we build a confidence interval, will it contain 5% inside of it somewhere? If so, shut it down. So we're going to build a confidence interval. All right, so let's do it in the 4 steps. Let me get another black marker. This one's starting to give out on me. Let's try this one. All right, step number 1, we need to find the z. Actually, before you begin, and I can't believe I'm kicking myself for not doing this first. Before you begin any word problem, you should make it not a word problem. Now, how do you do that? The trick to most word problems is most of the words are irrelevant when it comes to the calculations. They're only relevant when it comes to interpreting the final results. So if you have a word problem, a good strategy is to go through it and extract only the information needed to calculate the end result, which in this case is a confidence interval. The formulas are erased, but I'll put them back up here real quick. We really only have 3 formulas here. The standard error, which is the square root of p hat times 1 minus p hat, having trouble drawing my p hats, all over the sample size, which is all under the square root. The margin of error is z times the standard error, and our confidence interval is p hat plus or minus the margin of error. But if we trace our steps, we really only need 3 pieces of information: a z, a sample size, and a p hat. So let's extract the information that we're given and then process it to get the results that we want. The first number that we're given is 250, and that's the sample size. So we are given n equals 250. Let's see what else we're given. The next number that we're given is the 3.2%. And that is the percent of the sample that has a characteristic, the characteristic of being defective. So that is the value of p hat. This is different than the previous example where we were not given the percent, but we were given the information to calculate it. So in this case, p hat is equal to 3.2% or 0.032. Remember, percents are great for describing things, horrible for doing math with. The next number that we were given was the 99% confidence level. Is there a variable for confidence level? Not really. If you look in some textbooks, they will say the confidence level is represented as 100 times 1 minus alpha percent. And there's a reason behind it, but it so clouds what's going on. I really don't bother with it. The alpha, by the way, is something called significance level, which we'll talk about a lot when we get to hypothesis testing. But for our purposes, we'll just say confidence level equals 99%. I guess we could abbreviate that CL. Well, let's go ahead and write it as 99%. So this is what we're given. Every math problem, many math problems, can be boiled down to what am I given and what do I want to find. What I want to find is p hat plus or minus the margin of error. And now all we have to do is bridge the gap between the information that we're given and the information that we want to find using our formulas and knowing how to use the confidence level. So here's the work. And by the way, as a test question in my class, what I'm about to write is exactly what I would want to see on a test. Step number 1, we need to find the z, which means we need to use the confidence level. As a test question in my class, I would explicitly say sketch the bell curve representing the confidence level. So bell curve, 99% in the middle, 0 in the center, meaning that, that's the worst 9 I've drawn in a long time. My brain was already thinking percent when I got to the second 9. I can't let that go. My OCD refuses to. I don't know if I'm OCD, but it wouldn't surprise me. All right, so 99% in the middle, which means what percent is left over? 1%. But that 1%, in fact, I should go through the calculations real quick. The 2 tails is 100% minus 99%, which is 1%. And so 1 tail is 1% divided by 2, which is 0.5%, or as a decimal, 0.005. Be very careful converting it to a decimal. Why do we need that? Because we're going to use our z-chart to figure out these z's. And we know that the left area is 0.005. And because we're using our z-chart backwards, we want to think of this as a 4-digit decimal, so we'll put an extra 0 there. Then we will look that number up in the z-chart. Because it's a left area, it will tell us the z. The other one will be the positive. Now, silly me, forgot to get a z-chart out before I started this video. And because I'm filming this on my camera, I can't just pause it because that would end the video and I'd have to start another one. So I'm going to just hop into my computer real quick, which is right below my camera, serving as a power source for charging my camera. And I happen to be in where I need to be. Let's just go to Files, let's go to Distribution Tables, let's look up the Z distribution. You know, I've taught this class so long, I should know what this is, and when I look at it, I'm going to kick myself. If we use our z-chart, we're going to use negative 2.58. This area is dead center between negative 2.57 and negative 2.58. If you watch my videos from the previous week, I'm going to say 8, you know that when the area I'm looking up is dead center, I will always default to the larger digit on top. And by the way, now I can explain why. The true value of the z is somewhere between 2.57 and 2.58. By using the larger digit, I'm moving these z-scores outward slightly, which slightly raises the area in the middle and increases the confidence level. So really, 2.58 is associated with a confidence level just a little bit above 99%. But if I round it down to 2.57, I'm actually moving the 2 z's inward, decreasing the area in the middle, and lowering the confidence level to just a little below 99%. So if I'm doing statistics for a living and the person paying me to do it says, well, did you estimate this with 99% confidence? I don't want to say, well, not quite, but almost. Why didn't you do it at 99%? Because I had to round down. But if I round up, I can say, yeah, even better, a little bit more than 99%. So you don't ever want to lower a confidence level if you have the choice of lowering and raising. So by choosing the larger digit on top, it always raises the confidence level. All right, but anyway, part 1 is done. And as a test question, I would just really want to see the picture and the results down here. It's not necessary to do all this, but it doesn't hurt to write it down either. Just as a general rule of thumb for anybody watching this, especially if you're taking a math test. Well, not while you're watching this. When you give us stuff to grade, the less stuff you give us, the less chance we can give you partial credit if something goes wrong. We can only grade what you put down. So for example, if this were a test question and you wrote down the wrong z, I could give you no points for this. But if you drew the picture correctly, put the 99% there, put the 0.005 over there, and then had the wrong z, I personally would give you some points for that part of the question because you demonstrated you knew what to do with the confidence level, you just made a mistake with your chart. So the more right stuff on your test, the more possibility of getting partial credit if something goes wrong. And again, that's for me. I'm not speaking for all professors. Some are merciless and go, sorry, this isn't exactly what I have, you get nothing. But I digress. Step number 2 is to calculate the standard error. And the formula for the standard error is sitting right here. So let's go ahead and put it into the formula and see what happens. Again, as a test question in my class, it will say in the instructions, when you use a formula, write it down with the value substituted. In this case, our p hat is 0.032. So p hat times 1 minus p hat over the sample size, 250. Now, why would I want you to write that down on my test? Because if you make an error in your calculator, but you set it up properly, I can give you partial credit. And again, I can't speak for all math professors. I can only speak for myself. But I'm not out to get you. I'm not out to try to fail you. All I do is grade what you give me and see what happens. But I want to give you points for doing things correctly when you do them correctly. So the more information you can write down, the more possibility of getting partial credit if something goes wrong. Writing this down would be the correct thing to do. In my calculator, to 4 decimals, I got 0.0111. But since I was talking while I was doing it, let me do it again without talking. Got the same answer. If you got a different answer, I could be wrong, I make mistakes, but contact me and we'll get it figured out. But there's our standard error. The hardest part is over. Step 3, margin of error. Simply multiply the z, which was 2.58, times the standard error, 0.0111. I can do this without a calculator, but because it's just a bunch of ones, and I did number sense in high school. But to 4 decimal places, we're going to get 0.0286. Make sure I wrote that down correctly. Yes. And again, if somebody's watching this who's not in my class and you're like, that's not the answer, it's 0.028638. I know that, but the protocol I'm using on these is when you do a calculation, if it's more than 4 decimals, round it to 4 decimals. And finally, step 4. To create our interval, we simply take our p hat, which was 3.2%, or as a decimal, 0.032, plus or minus our margin of error, 0.0286. And let's see what that turns into. Do the subtraction, do the addition. And again, just so I don't accidentally make a mistake, as opposed to intentionally making a mistake, I suppose. The difference is 0.0034. But the sum is 0.0606. And since we're interpreting this in the context of percents, it goes from almost 0%, 0.34%, to 6.06%. So as a confidence interval question, here's our answer. Now, in the context of the word problem, should production shut down? The answer is yes. Why? Because our confidence interval centered at what we got from our sample at a 99% confidence level includes 5%. Remember, we're saying we are 99% confident that the percent of products that are actually defective is in this interval of values. Well, that interval of values contains at least 5%. Shut down production, recalibrate, run it again, and we'll test another sample. All right, but as far as actually calculating the confidence interval, very straightforward. Use the confidence level in the middle to find the z, use the formula for the standard error, multiply those two answers to calculate the margin of error, and then take your p hat, plus or minus the margin of error, boom, got your confidence interval. 4 easy steps.